Hi everybody. This is the second video for linear regression. In this video, I'm going to talk to you about correlation and something called the coefficient of determination and residuals. So this video is about lots of different tools that we use to figure out how strong the relationship is between your explanatory and response variables, as well as how good of a predictor our least squares regression line is, or how good a predictor our response variable or our explanatory variable is of our response variable. So first part of this video is about correlation. Okay, so correlation is essentially the relationship or the strength of the relationship between two variables, which is not something we can easily judge just by looking at a graph. So we needed a number, like an actual number, to denote how strong the relationship was between these variables. So whatever the variables are. So what we came up with for that is something called the correlation coefficient, which we represent with this variable r. Okay, so a couple of things about r. What this does is it measures the direction and strength of a linear relationship between two variables. It does not work for curved relationships. It only works for linear relationships. Okay, so if you were asked to interpret an R value, okay, then your interpretation would be the strength and direction part of the scatter plot description, right? So there is a strong positive relationship between these two variables. You just leave out the word linear because R only works with linear variables, okay? A couple of key things about the correlation coefficient. Most important thing is that R is always between -1 and 1. It cannot be greater than +1 or less than -1. Okay. So if someone says my correlation coefficient is 1.03, that's incorrect. Okay. A positive R means there's a positive association between the variables. A negative R means there's a negative association between the variables. Values near 0 mean the correlation is very weak. The stronger the relationship is, the closer the value of R will be to either +1 or -1. Okay. An exact perfect correlation of -1 or of +1 is almost impossible to achieve. That would be if every data point that you collected fell exactly on a line, like on a least squares regression line, okay, which most of the time that's not the case in the real world, okay? So, whoops, there we go. So what you see on both the left and right side of your screen is examples of scatter plots with their correlations below them, okay? So when we're describing a scatter plot or interpreting a correlation, the biggest question that I get from people is, okay, well, how do I know when this is a strong relationship or a very strong relationship, or like weak, moderately weak? Like, how do I know which is which? Okay. So the answer is we don't really know. Like, there's not a set value for anything in this range is strong, anything in this range is very strong. There's not really a range. Like, there's not an exact range that you have to memorize, right? But typically we say that we have a moderate relationship around 0.5, and then like that's the boundary, and then we have uh, I would say a strong relationship around 0.7 or 0.75. So, oops. So this right here, 0.5, I would say that's moderate. okay? Anything below that is weak, and then when the correlation is 0, that means no, no association. Okay, I would say that you can get to strong by about 0.7, maybe 0.75. But definitely if you can get to an R of 0.8, I would definitely say that that's strong, right? And then very strong, I would say you need your graph to look a lot like this one, where it's really, really close to an exact linear pattern. So I would say probably like 0.95 or above that would be considered very strong. Really, they're not going to dock you on the AP test if you call something moderately strong that's actually just strong, right? So if you're ever not sure, you can put that little wiggle word in there to help you. Okay. All right, so let's talk a little bit more about correlation and a couple of facts and then some cautionary tales here. Okay, so first thing, right? First thing is that correlation has no distinction between the explanatory and the response variables. The formula that we use to calculate correlation doesn't make any distinction between those variables, meaning you could switch your x and y variables and the correlation would be the same. Okay. The correlation is also resistant to change of units. So if you convert, say, height from meters to feet, that's not going to affect your correlation, right? But the correlation itself has no unit of measure. In the formula for correlation, typically what we're doing is we're dividing some x's and some y's, so the units end up canceling out. So correlation has no unit, okay? Key thing here, for which I mentioned already, is that one, the variables have to be quantitative, and R cannot be used to describe curve relationships no matter how strong that relationship is. Okay. Another thing that's very, very important is that the correlation is not resistant. Very much like the mean, right? It's very strongly affected by outliers. And it says a few outliers on here, but even just one outlier can very strongly affect the correlation. Okay. And R is not a complete summary of two variable data, right? So in order to get a complete summary, then you need a center and a spread, so mean and standard deviation for both of those variables, okay? The most important thing is that correlation does not mean causation, okay? That's the theme really of this entire unit, is that just because two things are related or it looks like they follow the same pattern, that does not mean that one variable causes the other variable to occur, right? Or causes the changes in that variable. The only way you can know that a relationship is causal is if you run an experiment on it and you randomly divide subjects into treatment groups, okay? All right, so that's a little bit about R. Give me just a second. I need to do some erasing and clear the screen, and then I'm going to talk to you about residuals next. Okay, so let's talk about residuals. Okay, so if you may have heard that term before when talking about money, that's at least the way that I've heard it, outside of a statistics classroom. So if you're talking about you have residual funds left over from something or residual supplies, that means the difference between what you expected you would need versus what you actually had left over. Okay. So good regression lines, good least squares regression lines. Make the difference between the actual data points and the predicted values from the least squares regression line as small as possible. Okay, so the reason that we have a least squares regression line is because that is the line that minimizes those residuals as much as possible. Okay, so those differences are called residuals. So the actual definition of a residual is it's the actual, or you may hear me call it the observed value minus the predicted value. Okay. So the observed value is the data point. Okay. So it's the Y value. The predicted value comes from the least squares regression line. Okay, the way that you remember this, okay, we are in an AP class, right? So the residual is actual minus predicted. We are in an AP class. All right, so the formula for a residual, let me increase this here so you can see this a little better. So the formula for a residual is resid, R-I-Z-I-D, R-I-S-I-D, residual equals y minus y hat. Okay, so remember, y is the actual value, y hat is the predicted value, right? That's what the hat is for, right? That means predicted, okay? Every data point has a residual. That residual is either positive or negative, okay? So the residual will be positive if the data point is above the least squares regression line. Okay. The residual will be negative if the data point is below the least squares regression line. Okay. So a positive residual means that you have an underestimation. Okay. Because what that means, the estimation is the value of the least squares regression line. So if the least squares regression line is below the data point, which is what's happening here for a positive residual, then that means that the prediction is an underestimation. Okay. Then a negative data point would be the opposite. A negative residual, if the data point is below the least squares regression line, that means the line overestimated the value of y, like the actual true value of y, for that particular value of x, okay? A residual is a very common thing that you were asked to interpret. So here is another script for you, okay? So essentially what you're doing is you're just taking the definition of a residual and you're putting it in context, okay? So the interpretation of a residual is the difference between the observed and predicted, and then you put your y variable in context, is, and then put the actual residual value, which is n, and then you put over or under, over estimation or underestimation. Okay. So this part, the difference between the observed and predicted, that's the definition of a residual. And then you're just stating what the actual residual is and then telling us if it is an over or underestimation. Okay, so what you can see now a little bit bigger on the left side of your screen is what these residuals actually look like. So we have all of these data points, right? The least squares regression line is there, right? It's the same one from the previous video, right? And you can see all of these vertical distances, right? Which is a deviation or a difference from the predicted value to the actual value, right? So these vertical lines are your residuals. So your least squares regression line is going to be created in such a way that those distances are minimized as much as possible. Okay. All right. Next little bit here, let's talk about outliers. Okay. So outliers don't show up a lot in statistics problems, like in these oh my goodness. In these scatter plot type problems, most scatter plot problems deal with interpretations of slope and residuals and correlation and all that fun stuff. Okay, but they do show up every once in a while. A very common question that's asked about outliers and about influential points, which I'm going to tell you about in a second, are about how adding an outlier or taking that away would affect the slope of the least squares regression line, for example, or the correlation value, etc. Okay, so an outlier, the actual definition of an outlier is it's an observation that lies outside the overall pattern of other observations. Okay. Um, Points that are outliers in the y direction but not the x direction have large residuals. Okay, so usually they usually have large residuals. Okay, um, right. So typically you're looking from a point that's really far from the least squares regression line, whether that point is kind of clustered in with the rest of the data, like it's within the x values that you're given, or the typical x values for the data, um, or not. Okay, influential points are a little bit different, but outliers typically are within the typical X value of the data that you have. They just have really large residuals. Okay, that's a little bit different from something that we call influential points. Okay, so we call a point influential if it's an observation that would, it says markedly on there, but I'm going to use the word drastically, which would drastically change the result of the least squares regression line slash correlation calculation if removed. Okay, usually has a large horizontal gap. Okay, so not necessarily something that has a very large residual, but rather something that has, I'm going to change this a little bit. Hold on. Rather, it's something that has a large horizontal gap between that point and the rest of the data. Okay, which you can kind of see here, right? So this is a perfect example. These points that are circled in red here, perfect example of influential points, because without those points, right, if we just eliminated these, right, that least squares regression line probably would have looked something like this. Like it probably would have been a negative slope. Right? So outliers can be influential points also, right? Like points can be both an outlier and an influential point. You kind of just have to look at it, okay, and figure out what's going on based on the graph. All right, so give me a second. One more time, I got to reset, and then I'm going to tell you a little bit about residual plots, and then we're going to talk about the coefficient of determination. All right, y'all. So let's talk about residual plots. Okay, residual plots, what they are is they show the x variable versus the residual value on the y-axis. Okay, so that's what a residual plot is. Essentially, what you're doing is you're taking your line of best fit, right? And then turning it so that it's horizontal. And that essentially is going to give you those residual values, right? Um, the goal is for residuals to be small, right? So one thing you can use residual plots for is to see if your line, your least squares regression line, is really the best line to draw because it will minimize your residuals, right? So you won't have large distances between the line, the zero axis, and the data points, right? Because the data points are plotting the residuals, right? One other thing that I want to make sure that you know about residual plots especially is that they typically start the or rather the horizontal axis is typically in the middle of the graph so that way you can show both the positive and negative residuals, okay? Another thing that residual plots are great for is figuring out if a linear relationship is appropriate for the data set. Okay, so if there is no pattern in the residual plot, then that means a linear model is appropriate for the data. Okay. Okay, so you can kind of see that. I'm going to zoom in a little bit on this side, but you can see that here, right? So this is my residual plot. There's a very obvious curved pattern here, right? And if you convert that back to what the actual data looked like, you can see that a linear relationship really was not the best relationship to use for this particular data set, right? A curved relationship would have been much better, okay? Right? Then residuals also have a standard deviation, right? So standard deviation exists for residuals as well. Okay, but it's not exactly, well, okay. It's not exactly what you're used to when you hear the word standard deviation, but it's pretty close. Okay, so when we're talking about regular standard deviation in a in a regular data set as a measure of spread, remember that standard deviation is the average distance of your data points from the mean, right? That's the general definition of standard deviation. So standard deviation of residual is the average residual value or the typical residual value. Okay, so standard deviation of residuals tells us how far our least squares regression line predictions will be on average from the true value, right? Like the data points, right? So it's your typical residual value. Okay, and then we also have an interpretation, which I did not give you enough space for down here. But if you are asked to interpret the standard deviation of the residual, you're basically just going to use you're essentially just going to use the definition there. So your interpretation, your script for the interpretation of S, which is the standard deviation of residuals, is on average the difference between the predicted and observed values, you could say true values, of y variable in context is, and then you just say what the actual number is, S with And then the unit on that is the unit of the y variable. So y variable units. Okay, and we're going to get a chance to do that here when we get to the end of this video, because I have an example problem for you that goes through all of that. Okay, now you may be looking at this screen and going, oh my God, look at that crazy formula for standard deviation of the residual. Okay, lucky for you, that formula is one, given to you on the AP Stats formula sheet, and two, almost never will you be asked to calculate a standard deviation of residuals because it just takes too dang long. Just like you rarely will ever be asked to calculate by hand a standard deviation because it's just going to take too long. Okay? Most of the time, all you'll have to do with the standard deviation of residuals is to interpret it. So using this interpretation right here, okay? Right? So we want that standard deviation, that S, to be low because that means that our residuals are fairly close or fairly small. So that means that the difference between our predictions and the actual true values are not super, super large. Okay, so we want that value to be small as we can make it. Okay, so what you see on the left side of your screen here is an example of a residual plot. Right, so the line in the middle is the horizontal axis. So we can see here that we've got some positive residuals and some negative residuals. I would say that this data point right here, this data point here looks like an outlier to me. Right, because it has a very large residual, especially compared to the other data points. Right, so that one's probably an outlier. Right? So here, if you were asked, like, is a linear model appropriate? Here, I would say, yes, a linear model is appropriate. All you have to say is that the residual plot has no obvious pattern. So a linear model is appropriate, or I wrote a good choice here. All right. Okay, so give me another moment. I have to clear my screen off. Whoops, and I'm getting a call. So let me clear my screen off quickly, and then we're going to talk about coefficient of determination, and then we'll bring it all together in one like practice example problem at the end. All right, y'all. So let's talk about the coefficient of determination, which is a very, very fanciful term for something that you don't really need to know a whole lot about. It's more important that you understand how to interpret it, right, and kind of what it does. So the coefficient of determination is r squared, okay, which is the correlation coefficient. So it's whatever number you get for correlation, the decimal value squared. Okay, so what the coefficient of determination does is it tells us the amount of variation in the y variable, that can be explained by changes in x, right? And not some other confounding variable. Okay, so essentially what we're talking about here is, if you think back to Unit 1, when we were learning about studies and experiments, right? Especially when we were learning about experiments, what I told you in the design of a good experiment is that it eliminates as much confounding as possible, right? But whenever you're looking at the relationship between two different variables, then you are likely going to come across a third variable that will affect the changes in the y variable, that will affect that is not the x variable, right? So what R squared does is it tells us how much of the variation that we see in the response variable can actually actively be attributed to us changing the X variable, okay? X is not causing Y to change. That's not what this is saying, right? We're just trying to figure out how much of the variation and change in the Y variable can be accounted for or explained by the changes that you see in the X variable that are mapped out by the least squares regression line. Okay, because that X variable may not be the only variable that's creating or related to those changes in the Y variable. Okay, if all of that in your head is going like, I'm not sure if I can remember all that. Here's the thing: you very rarely, if ever, have to do anything with R squared other than maybe calculate it or interpret it. Okay, if you memorize the script for the coefficient of determination, you will get these problems right every single time. Okay, so here is your script. You would type the R squared value, whatever it is. Okay, so R squared percent of the variation in the Y variable in context. You can either say is related to, or you can say can be explained by the variation in the X variable in context. Okay, so for example, right? So for example, let's say we were looking at our price and miles driven data, right? So let's see, did they give us a correlation value for that one? I don't think so. So I'm just going to make one up. So let's say, oops, scrolled too far. So let's say that we had a R value of 0.85. So that means my R squared value is 0.85 times itself, right? So you have to take that value and actually square it. So 0.85 times 0.85 is 0.7225. Okay, so the way that I would write this, and remember this is for price, the price of a car and the miles driven. So I would convert this number to a percentage. So I would say 72.25% of the variation in price is related to, or you can say can be explained by, the variation in miles driven. Okay, price could be affected or related to lots of other different X variables, right? For a used car, it could definitely be how many miles is on it, but it could also be how old the car is, or what the make and model of the car is, or how many previous owners it had, or a variety of other things. So we're saying that in this example that about 72% of the variation that we see in price can be explained just by looking at the miles that the car has on it. Okay. Just like R squared has this very fanciful formula that is not something you have to know or memorize. Like I said, rarely, if ever, will you be asked to calculate R squared just because it takes too long. Um, every once in a while, you might be asked to calculate R, And there is a formula for that, which I'll show you in the next video, but it's very rare. What you will see, and what I'm hoping that you're seeing throughout all of these videos, is that a lot of what's happening with least squares regression is that you're taking values that are given to you in like a calculator or a computer output, and you are interpreting them or using them to make predictions. Okay, that's what we use most of this for. Okay, so there's a problem here that I would love for you to try. Okay, so we have we're going back to our number of points scored per game with these basketball teams and then the number of wins. There's a plot here with the least squares regression line as well as the residual plot. And then I also gave you the equation of the least squares regression line. So I want you to try these out here. Okay, so the first is to calculate and interpret a residual for South Carolina. Okay. Really quickly, in order to do that, remember X is 11 here. Okay. The 31 points per game. Oh, sorry. I have that backwards. Apologies. Okay. The wins is your actual Y value. It's like your actual value. Okay. 30.1 points per game is your X value. You have to calculate Y hat using the least squares regression line down here before being able to calculate the residual. Okay. And then these other three questions come directly from your word formulas, your scripts, right? So go back, find the scripts, and see if you can do these 4 problems here. Okay, so give those a go and then check back with me and we'll see how you did. All right, y'all. So let's take a look and see how you did here. So my calculation of my residual for South Carolina, I had to figure out, before I did anything, I had to figure out what the predicted value was, because you can't figure out a residual without both the actual value, which is what you have here, right? The actual value and the predicted value, because remember that the residual is the actual value minus the predicted value. Okay, most of the time these problems will give you the actual value and you have to use the least squares regression line to calculate the predicted value. So that's exactly what I did. I plugged the X value that they gave us, 30.1 points per game, into my least squares regression line and got 9.4037 wins. Then subtracted 11 and 9.4037 and got 1.5963, and I really should have put a unit here. Wins. Okay, and then here is my interpretation, which I know the text is kind of small. Okay, but there's the interpretation. The difference between the observed and predicted number of wins for South Carolina is 1.5963, which is an underestimation. Okay, for number 2, this asked, is a linear model appropriate? All you have to do is look at the residual plot and say, is there a pattern? And I'm going to say, no, there's no obvious pattern here. So a linear model is appropriate because the residual plot shows no obvious pattern. Okay. 3 is to interpret the value S equals 1.24. So remember, that's the standard deviation of the residual. So your script is on average the difference between the predicted and observed Y variable, number of wins, is S value with Y, with the Y variable unit. So 1.24 wins. And then I put under here, just as an aside or a little note for you, okay, basically what you just said is the average residual is 1.24 wins, okay? And number 4, the last thing here, is interpret the value R squared equals 0.88. So I'm going to convert that to an actual percentage. So 88% of the variation in number of wins, right, Y variable, is related to, or you could have said is explained by, the variation in points scored per game, your X variable. All right, y'all. I know this video has been kind of long. Thanks for sticking with me through the whole thing. The next two videos will be a lot shorter. I'm going to show you how to use the computer output, as well as talk to you a little bit about transforming data that is not linear. So I will see you in the next video. Bye, everybody.